Okay, so assignment 3 was due today, and there'll be no assignment next week because on the Thursday, the October the 9th, is your midterm. Now, unfortunately, as you know, last week all your assignments were wiped out on BSpace, and we asked you to resubmit by Friday. However, some of you submitted over the weekend. I'm not sure why this happened. Yeah? That's not true, as far as I remember it, but given that it could be a misunderstanding, yeah? Huh?
I went back because I was
okay. Okay. Well, given that there was a misunderstanding, we're going to give you leeway, and that's fine. But these deadlines apply, and if you haven't handed it in already by today, then you get 0. And this applies for all assignments in the future. So because of the misunderstanding, that's fine. But those of you who didn't hand in by Monday, of course, will get a 0 for it. So these assignments have to be done on time. Any questions about that? Okay. So on Thursday a week, you'll come to the classroom here and bring one blue book with you, a large one. And I'll ask you to exchange the blue book with somebody sitting near you, because I'm going to give you prepared questions that you prepare ahead of time in your mind, not on a sheet of paper. You can prepare on a sheet of paper to study it if you want. And but the exam, the midterm is going to be on the first 11 lectures. So that's up until Thursday. So it's today's lecture and Thursday's lecture. And make sure you know the following. So you need to know the differences between the discrete and continuous models in one dimension that we've talked about, the general ones. And you need to know how to characterize the stability, how to find the equilibrium and characterize the stability. You need to know the basics of the genetic models, and along the line of the example that you saw in your work set, I will ask you to derive a model similar to that. So you can also check problems 40 and 41 in your calculus text. And then you should know the basic ideas of the host parasitoid model. I'll probably ask some questions on that. And I will hand out a sheet with about 4 or 5 pages in it, and you'll answer your questions on that sheet of paper. And then there will be a couple more questions that you'll answer in the blue book. Well, actually, there'll be 3 questions that you'll answer in your blue book. And this is one of the questions that you'll answer, so I've already told you about this. Okay, any questions about the midterm? So remember, you only have to get 80 out of 100 to get an A, yeah? It's up to the GSIs, so there's no homework assignment for next week. So I would say the sections on Friday and Monday will probably be some kind of revision. Or you can bring your questions. Is Eric going to be able to come? Do you know, or what's up with Eric? Okay. Okay. So Colin's going to stand in for Eric, and then later in the year, or in the semester, Eric will stand in for Colin. Okay? Are there any questions on the material from last week? Okay. So for today, most of the material you'll find in this article, Gets Harvesting Encyclopedia 2012, and my lecture notes. And what I'm going to do today, I'm going to develop something called Beverton Holt yield per recruit analysis, which also in some of the texts you might find called cohort analysis. I'm going to develop this material on the board, so I'll shut this off for now, and I'll come back to talk about some of these diagrams that I have here at the end of this material. But to begin with, we'll develop the basic model on the board. Okay. Yeah, thanks. So I'll put this up and turn off the computer so we can use all the board space we want. I guess I have to blank the screen here. Okay, great. So up till now, what we've done is we've modeled the population in terms of either numbers or biomass, but not both. And each population has been represented by a single variable, either x or n. Now what we're going to do is we're going to consider a cohort of individuals. Let's see, I'll use my own. So we're going to represent this cohort using 2 variables. N of t is going to be the number of individuals. And we start the cohort off at time 0 with n at time 0, either n subscript 0 or sometimes we'll give it the name R. And you'll see this name R come in for recruits. So we've used R before for population growth rate, but in the context of this theory, you'll see R in terms of the number of recruits that we start out with. So N of t is the number of individuals at time t, and W of t is the mass or weight of each individual at time t. So this model that I'm going to show you applies to a model where we want to maximize the biomass of the cohort. And so if each individual weighs W of t and N of t are the numbers, then X of t, if that's the total biomass of the cohort at time t, what is X of t? How are we going to calculate X of t? Okay, yeah. So we have NT individuals, and each one weighs W of t. Now, how do we expect N of t is going to change over time? It's going to start out here at N0, which I'll call R. How is N of t going to change over time if no new individuals come into the cohort? what can happen to them? What's the only thing that can happen to each individual? They can die. So what's going to happen to the numbers over time? It's going to decrease, okay? Okay, and so we're going to make some rather simple assumptions about W of t. Each individual's weight. What do you think is going to happen to the weight of an individual over time? So if you're dealing with something like a fish keep growing until they die. What do you think is going to happen? Keep going up, okay? So we'll start out at W0, and each individual will keep increasing. Then we can make some assumptions about W of t. We can assume that there's an upper valued W bar, is what I called it. Or W max in my notes. So let's call it that. Okay, so each individual is going to get bigger and bigger, but somehow it approaches the biggest possible size that it could be. Now, of course, this is not necessarily a perfect assumption for a lot of animals, where as they age, they may get to a point where they start to lose weight as they age, but it's a reasonable approximation. So if we're going to plot x of t as a function of time, is x of t going to increase or decrease as a function of time? What do you think? So what's going to happen initially? N's going down, but W is going up. So it depends on the relative steepness of this curve compared to the relative rate of decline of this curve. If W of t is increasing faster over here than this curve is declining over there, then initially it'll start to increase. Then what happens is that after a while, N of t will decline, and W of t will level off. So that means the population, the amount of biomass will start to decline. As individuals keep dying, but W of t is leveled off. So in that case, we can expect to start out at x0 and start to increase, and then over time start to decrease. Of course, if the initial growth is slow over here and the initial rate of decline is high, then we might get something that looks like this. So it doesn't necessarily have a maximum. Now what we're going to do is we're going to study this problem, and we're going to have a look at the parameters that define this curve and the parameters that define this curve, and we're going to try to find this maximum. Now imagine this is an aquaculture facility, and we have a pond, and we put a bunch of small fish into the pond at time 0. We put R of them in, and then we feed them, or there's natural food, but also predators that will come into the pond. Some will die of natural causes of disease, parasites. Some will die from predators, maybe birds, whatever. And so there's going to be a decline, but also individual fish are going to grow bigger. And if the decline is sufficiently slow initially and the growth of the fish is initially large enough, then we'll have this situation. So if we want to maximize the biomass or the production from this pond, this aquaculture facility, then we can come to this point over here, and we can remove all the individuals there, and we'll get the maximum biomass that we can. Now, we know from our discussions that that's not necessarily economically the best thing to do. Why, from an economic point of view, might we not want to wait until this point to harvest all the fish? Let's say we could just drain the pond and go in and remove them by hand, pull the plug, and then gather them up and then fill it up with water again and redo it. Or we could take a huge big net and pull it right through the pond and get everybody out in one go. Why might this not be a good idea? Yeah? Okay, so that's a very good point. However, in a facility like this, there'll probably be another pond over where you just got a small breeding population, and they'll lay lots of eggs, and then you go in. And so you'll get it from elsewhere. So that's a very important connection that you have to make if it's not an aquaculture facility. But if it is an aquaculture facility, then you can separate out those functions. From an economic point of view, a present value point of view, why might you not want to wait until that? Well, yeah. Okay, if there's a cost in running this facility, so the cost may be very small because it's not like running a boat or anything, especially if we're not adding feed. So from a discounting point of view, why? Or from a time point of view, are we interested in maximizing harvest, or are we interested in maximizing harvest per unit time? Yeah? Right. Right. So that's like the forest stand management problem. You don't wait until you maximize the mass that you get out, but you have a solution of mass per unit time. So you could do this like a forest stand management problem if you wanted to solve that. But we're going to look at it from a slightly different point of view. In the forest stand management problem, we didn't think of the trees as disappearing one by one as time goes on. Yeah, in the forest stand management, the value just went up asymptotically. It might have reached a maximum, but it didn't have this very pronounced situation where after some point, the fish are growing sufficiently slowly from one time period to the next, but the probability of dying stays up relatively high, so we need to harvest the population. So when we look at a problem like this, the first thing I'm going to do is I'm going to try and solve for this point. Because if you remember, when we did our yield per recruit analysis, when we did our general equilibrium yield analysis for the Schaefer fishery, we first just looked at yield. So we're going to first look at yield, and we're going to try and maximize the biomass. So when I talk about maximizing the biomass, I'm not taking any economic considerations into account. It's just the first step to understanding this problem. Do you have a question? Uh-huh. Yeah. Right. Right. It is. So we're going to do that. So that's very good. You want to come do it? You're good. Okay. So that's good thinking. That's exactly how we're going to proceed. So we want to maximize this quantity. how do you find the maximum point? So the first thing I'm going to do is I'm going to give you the mathematical challenge of finding the time when this occurs. I'm not saying that from an economic point of view it's the best time, but mathematically we can define the problem, find that time. It's the first step. So how do we find the time when the maximum occurs? What do? You take the derivative. Okay, so dx dt, which is equal to d by dt of w of t, n of t. Okay, so how do we differentiate a product? We use the product rule. Okay, so that's w of t dn dt plus n of t dw dt. Okay, so that's the first step. Now, if we want to find a maximum, what do we have to do to that equation? We have to set it equal to 0. So maximum will occur when dx dt equals 0. So remember, when dx dt equals 0, we have a stationary point which could be a maximum or a minimum or some sort of inflection. However, if it's a maximum and if it's interior to the interval, then this derivative condition applies. So if this doesn't make sense to you, you've got to go back to a calculus textbook. You can go back to the textbook for this class, and you can have a look at finding maximum and minimum, and you can have a look at that section. Okay, so that means we can reorganize this equation. So dx dt, that implies that w of t dn dt is equal to minus n of t dw dt. Now, provided w and n are not 0, which is a reasonable thing to assume, because if they're 0, the cohort is 0, the biomass is 0, we can divide through, we can say 1 over n dn dt is equal to minus 1 over w dw dt. Now, dn dt, if this is a simple exponential decay, then what is the equation for dn dt? So in the simplest case, if this is just exponential decay, what is the equation? dn dt is equal to minus alpha n. And that would imply that n at time t is equal to n at time 0, e to the minus alpha t. And that would just be simple exponential. What is the implicit assumption? If we say that that models how n is going to change, what are we assuming about the population? There's an implicit assumption. Yeah. Lambda. Well, this says that the rate of change of n is proportional to n. It's negative, but it's a constant. So what does that mean? In each time interval, any individual has an equal chance of dying, and it's not a function of time itself, and it's not a function of n. So the per capita decay rate is a constant. Yeah? Would this mean ETH? Yeah. Well, if you go back to what we said about the exponential model, I said that if I say this, it's this, and if I say this, it's that. And that's like way back. So you've got to keep these things. This is going to become second nature to you, this statement. This statement appears at least in 10 different places in this class. And so it's important to remember that. Okay. So that's how n is changing. And what it says is that in any interval of time, the probability that an individual dies is constant. Is that reasonable? What do you think? I got a bit of a cough, so I'm just going to take some cough drops. No, it's not reasonable. Why is it not reasonable? Well, so very old specimens are perhaps more likely to die. But if it's birds coming down to prey, it depends on the size of the bird and the size of the individual. If it's a small bird, it can take a small fish. If it's a large bird, it can take mainly a large fish or a small fish. So it may be that smaller fish are more likely to die, or maybe larger fish are more likely to die. They're different life history patterns. So in humans, what's the situation? Are you more likely to die when you're small or when you're big? Small and old. So big and old, you actually start to shrink as you get older. So humans don't fit this growth function very well. But that's a problem. But anyway, this is the assumption. And so we're going to go with this assumption. So that means 1 over n dn dt is equal to minus alpha. So this equation implies that 1 over w dw dt is equal to alpha. So this point here on this curve is going to occur when this curve w of t divided by 1 over w is equal to alpha. Now, w of t is greater than